Hi everyone. In this lesson, I'm going to first address the important issue raised in previous lessons. That is, how to apply or extend Eshelby's approach to real rocks. I will then briefly introduce our multi-scale approach. My treatment here is brief. The intention is to help you read the lecture notes and the referenced papers if you wish to learn more about the subject. First, let us briefly review Eshelby's solutions. Eshelby's solutions are summarized by a set of partitioning equations. The local fields are related to the macro-scale fields by this set of equations. Lowercase symbols represent the partitioned fields. Equivalent uppercase symbols represent macro-scale fields. Pi and S are Eshelby tensors. A and B are strain rate partitioning tensor and stress partitioning tensor. These three partitioning equations are fundamental in micromechanics. The set of partitioning equations can also be recast into a set of interaction equations. The stress difference between the local field and the macro-scale field is related to the strain rate difference by this equation, and the vorticity difference is related by this second equation. And these two equations are called interaction equations. They can be derived from the partitioning equations by inserting the stress-strain rate relationship into these equations. So the interaction equations are often written in a more succinct form. Sigma with a wave on it stands for the stress difference. Epsilon with a wave on it stands for the strain rate difference. H and H arc are new tensors introduced to make their expressions more succinct. So the partitioning equations and interaction equations are equivalent. Using these newly introduced tensors, the strain rate partitioning tensor and the stress partitioning tensor can be written in these expressions. They are both succinct and parallel in form. As elegant as they are, the partitioning equations are applicable under strict assumptions, and these assumptions include: first, both the matrix and the RDE are supposed to be either linearly elastic or linearly viscous. The inhomogeneity is assumed to be ellipsoidal in shape. The matrix is assumed to be infinite in extension, and finally, the matrix is rheologically uniform. Now, none of these assumptions appears to be applicable to real rocks. So we have to ask the question, how can we use these partitioning equations to real rocks? Let us now address these assumptions one by one. First, the nonlinear rheology issue. This is dealt with by what is called the linearization approach. The linearization approach applies to all nonlinear behaviors, and I am going to use a special nonlinear behavior, that is, power law viscous behavior, to illustrate the principle of linearization. So in the simple shear setup, the shear strain rate, gamma dot, is related to the shear stress by this nonlinear relationship. A is a parameter dependent on the composition of the material, pressure and temperature of the deformation, and the fluid activity, etc. N here is the stress exponent. So for rocks and minerals, N is usually greater than 1. For dislocation creep situation, N is usually between 3 and 5. For a power law viscous material, it doesn't have a fixed viscosity. In session 2, I introduced the concept of effective viscosity, which is defined as the ratio of stress to the strain rate in the simple shear situation is tau over gamma dot. Of course, the effective viscosity is not a fixed value because it depends on the stress state. For this power law relationship, the effective viscosity is related to the stress by this. You can easily obtain this relationship using the definition of the effective viscosity. In a plot of shear stress versus shear strain rate, the power law relationship is represented by this purple curve. The effective viscosity at a stress state, tau alpha, is defined by the slope of this dashed blue line. In materials sciences literature, the effective viscosity is often called the secant viscosity, and you can understand why it is named so, because it is a straight line intersecting the curved purple line. Another useful concept is called tangent viscosity, which I also introduced in session 2. The tangent viscosity at a stress or strain rate state is the slope of the tangential line of the nonlinear relationship. So for this power law relationship, one can easily obtain this relationship. So the tangent viscosity, eta tan, is the effective viscosity divided by the stress exponent. It is clear that the tangent viscosity is also not a fixed value. So if you move to another stress and strain rate state, you get another tangent viscosity. Tangent linearization leads to a straight line that has an intercept at strain rate 0. As you can see, in the neighborhood of stress-strain rate domain, we can use this linear relationship to actually approximate the nonlinear relationship. That is the idea of linearization. So here is the linearization explained in more detail for the general situation. The tangent relationship leads to a tangent viscosity, which is the slope of this dashed line, and also a back-extrapolated stress term. In the more general case, the nonlinear rheology is represented by this stress-strain rate relationship. This nonlinear relationship can be written forcefully into this pseudo-linear form. That is the concept of effective or secant viscosity, or effective or secant compliance. The linearization approach is to look for a linearized relationship, stress linearly related to the current strain rate in the neighborhood of that strain rate state. So we found a linear relationship to approximate the nonlinear relationship in the neighborhood of a stress-strain rate state, and that necessarily leads to a back-extrapolated stress. Or if we use the inverse relationship, that leads to a linearized compliance and a back-extrapolated strain rate term. The linearization is carried out for both the inhomogeneity and also the surrounding matrix. With that linearization, the original partitioning equation, strain rate partitioning equation, and the stress partitioning equation can be reformulated into this form. Most RDEs are, of course, not perfectly ellipsoidal. However, it is a common practice in material sciences and earth sciences to regard RDEs as ellipsoids. Ellipsoids can be made to approximate many different bodies by changing their relative semi-axis length. For instance, a rod-like object can be approximated by a very elongated ellipsoid. A Ramsey-type shear zone may be represented by a penny-shaped ellipsoid. So ellipsoids can be made to mimic real geometry. It has been confirmed both theoretically and also experimentally that the rotational behavior of RDEs can be always represented by an effective ellipsoid. When the RDEs are non-ellipsoidal, the partitional fields in the RDEs are not uniform. However, the Eshelby solutions can be regarded as averaged field inside them. There is a theoretical investigation in 2 dimensions which has confirmed that using the Escherbi's solutions as the average field is valid as long as the non-ellipsoid inclusions are convex in shape. So we have to be mindful, of course, if the RDE is far away from ellipsoidal shape, particularly when the RDEs are really non-convex. The issue of RDEs in finite space is dealt with by the condition of scale separation. Of course, Escherbi's solution requires that the inhomogeneity is embedded in an infinite matrix. In reality, we would like to deal with the relationship between the local fields, the partition field, and the boundary conditions at the representative volume element scale. As long as the RDE is much smaller than the representative volume element, the RDE can be practically regarded as an inclusion embedded in an infinite matrix. Of course, we have to be always mindful that the scale of separation condition is satisfied. It can be said that the scale separation is varied for many geological problems. For instance, the ductile deformation of a shear zone, the development of malonites. In this situation, the inhomogeneities are below millimeter scale, and the relevant RVE, representative volume element, is usually on decimeter or even meter scale. So there are orders of magnitude separation in the scale of their inhomogeneities and their representative volume element. Escherbi's solutions also assumes that the interface is coherent, that is, there is no free slip along the interface between the inhomogeneity and the matrix. However, as I will show in the next slide, slippery interfaces are likely very common in rocks. Slippery interface means that the interface is not coherent. In the extreme situation, the interface is totally lubricated. The deviatoric stress in the matrix cannot be transmitted into the inhomogeneity. The stress state in the inhomogeneity has to be perfectly hydrostatic. There is microstructure evidence for slippery interface in rocks. Theoretical predictions are that elongated, rigid objects may either rotate with the vorticity or reach a stable position at a small synthetic angle with respect to the shear boundary. The behavior is dependent on the aspect ratio of the object and the vorticity number of the flow. However, synthetic clasts are rare in rocks. Most commonly, rigid clasts are aligned at a small angle antithetic with respect to the shear plane. Like in this malonite, the sense of shear here is top to the left. Most feldspar porphyry clasts are aligned with the long axis at a small antithetic angle with respect to shear zone. Synthetic porphyry clasts are rare. So the theoretical prediction is this. The real observation is like this. Most clasts have a small angle antithetic with respect to the shear plane. Natural observations of malonites, like this one from a Metagabro malonite. The porphyry clasts are mostly antithetic with respect to the shear boundary. So the positive angle here means antithetic. Most of these porphyry clasts are antithetic. Mica fish in malonites are almost entirely in the antithetic orientation. So there is a major discrepancy between theoretical predictions and the natural observations. And this discrepancy can be explained by the slippery interface. The reason for the slippery interface could be many, but most important is probably due to fine-grained materials and the fluid activity along the interface. So the consequence of a slippery interface means that the effective viscosity of the RDE is much reduced. So there are ways to deal with the interfacial slip. That is by using a very lower effective viscosity. The matrix is almost never perfectly uniform in nature, and this is dealt with by a hypothetic homogeneous equivalent medium. In this approach, the heterogeneous matrix is replaced by a hypothetic homogeneous equivalent medium, HEM. HEM may stand for slightly different things in different papers. H is always homogeneous. E can stand for either equivalent or effective. M means matrix, medium, or material. Regardless, the concept is the same. That is, we use a hypothetic uniform material to approximate the actual heterogeneous matrix. The rheology of HEM is obtained by a homogenization method, which we discussed in the previous lesson. And homogenization equations are also formulated in terms of Aschenbach's approach. Of course, using HEM, a hypothetic uniform material to represent the actual heterogeneous matrix, is a simplification, what is called the mean field method or the mean field approach. In our previous lesson, when we discussed the homogenization, the discussion was based on linear rheology. Nonlinear rheology means that iterative computation is necessary. The reason is actually simple, because to solve the partitioning equations, we need to know the stiffness of the effective material, whereas the stiffness of the effective material cannot be determined until the partition fields are solved. Because of this, these two equations must be solved simultaneously and iteratively, and that is the so-called self-consistent solution. Our self-consistent solution is called multi-order power law approach. Multi-order because we are dealing with macroscale flows and microscale flows. Power law because we are dealing with power law viscous rheology. The approach was first presented 10 years ago. It was completely developed in these two papers. The approach has since been used and improved in a few PhD theses at Western University. MATLAB programs have been fully developed on the basis of early MathCAD algorithm. Our self-consistent algorithm is illustrated by this flowchart. The input is the macroscale flow field and the initial states of all the RDEs. The computation is achieved by an outer loop for homogenization and nested inner loops for partitioning. Starting with an initial case of the HEM rheology and macroscale stress, partition flow field in an RDE is calculated in an iterative inner loop. The iterative computation continues until the partition flow field converge within a prescribed tolerance. The partition computation can be done by parallel computing because the calculation for every RDE is independent. When the inner loop computation is completed for all the RDEs, the HEM rheology and the macroscale stress are updated, and the updated information is used for the next round of calculation. The outer loop calculation continues until both the macroscale rheology and the macroscale stress converge within prescribed tolerance. When that is achieved, the system is updated with new RDE states, new HEM rheology, and the system is ready for the next step of computation. The partitioned flow fields and the HEM rheology obtained this way can be exported for the investigation of fabric development in selected RDEs, such as the shape-preferred orientation fabric development in the RDEs, like L-tectonite development, foliation and lineation geometries. We can also investigate LPO development in selected RDEs, such as quartz CPU development. We can use the partition flow to investigate other geological problems. So by this approach, we relate self-consistent solutions with multi-scale modeling. We achieve multi-scale modeling and multi-physics coupling. The Moplar package is available via this site. The element-in-element approach can be used more generally. Our Moplar approach can be nested into a finite element model, for instance. A finite element model for lithospheric deformation can extend many hundreds of kilometers, and each element can be many cubic kilometers. The finite element model generates truly macro-scale flow fields, and we can select the macro-scale flow field in some elements to be used as input for our Moplar calculation. Our Moplar calculation can then be used to calculate downscale flow fields, which can be further used by models such as VPSC. So in doing this, we truly achieve modeling of many scales. We couple different models. We also couple multiple physics, from flow analysis to the development of lattice preferred orientations. As I said at the beginning, the treatment in this lesson is a brief introduction. Please read the lecture notes and the referenced papers for more details. Thank you for your attention.